Okay, I'm going to start with a quick recap of what we did last time. Let's see. So, today, well, previous lecture and today's lecture, we talked about moment of inertia. And we basically asked ourselves, okay, how can we determine if we have a beam, why a certain orientation is better in bending than another orientation? And the idea that we used to quantify that was the moment of inertia. And basically what it means is the moment of inertia quantifies how much area is basically the furthest away from our bending axis. And that concept is what we call the moment of inertia, or the area moment of inertia, the second moment of inertia, or just the second moment of inertia. So there are different names for it as well. So just keep that in mind. How I will call it in the lecture series, I just call it moment of inertia, and I refer to the second moment of inertia. So there are multiple moments of inertia depending on the application. So for example, if you like in polar coordinate or torsion, then you're basically talking about a polar moment of inertia, but you still call that moment of inertia because it's just simpler to discuss. So based on your application, you can have say different formulas, but all of them are referred to as moment of inertia. Technically, they all have slightly different names, like the area moment of inertia, first moment of inertia, second moment of inertia, the polar moment of inertia, etc. With that said, and with this moment of inertia quantity, we could basically get a quantitative result of value to why certain geometries are better in bending than others. And we saw that if we basically put it on a landscape mode, say our 2x4 on horizontal, and we say that baseline, we can call that moment of inertia equal to 1. And if we just flip it by 90 degrees, like vertical, then we see it's actually 9 times better and resistant to bending. And then if you change the geometry a bit, but keep the same area present, we can see we can even make it more efficient into bending, and that's the I-beam. And we also mentioned like the moment of inertia is not a unique property of the cross section. It's basically determined is a value given with respect to a certain axis. So if you change that axis, your moment of inertia value will change as well. And then we got into how do we calculate it. We said, well, let's take an element of A and let's square it to x-axis with y squared. And then if we sum up all the small contribution of this small elements dA, so we get a whole contribution of the area, we can basically take the integral format, and then we define the moment of inertia as Ixx is equal to the integral over the area of y squared dA. And similarly, we can do that for the y-axis, so we get x squared dA. And we also note that since it's basically integral over the integral of the area, and we have the x and y coordinates squared. If we look at the units of the moment of inertia, it's always to the power of 4. So that's also say a common sense check that you can do for yourself to make sure that you did it correctly. If the units are off by just doing a unit analysis, you can see if you did something wrong or not. So it's always to the unit of to the power of 4. So millimeters to the power of 4, meter, feet, or inches to the power of 4. And then what we also discussed, like that the moment of inertia in x and y, because of the square root in the equation, will always be positive. The same, however, cannot be said of the moment of inertia on x and y, and that reason is because the coordinate system of x and y are defined based on your centroidal based on your axis system. It can be the centroidal axis, but it doesn't have to be. And then if you look at the coordinate system, say if you look at my mouse in this coordinate system, the quadrant 1, x and y are positive, so the moment of inertia will be positive. And quadrant 2, x and y, x will be positive, y will be negative, so we get a negative, and then we get negative, negative, which will yield positive, and then we get a negative, positive, which will yield a negative as well. After that, what we did, we basically looked at a simple cross section, rectangular square, a rectangle, cross section, and then we evaluated the moment of inertia using the integral format around the centroidal axis. So this is point C. And we see that the bounds of integration for the x-axis goes from minus b over 2 to plus b over 2, and the integration bounds for the y-axis goes from minus h over 2 to plus h over 2. Then we can evaluate that and we can get expression for our rectangular cross section. And if we do that, if we do the integration, what we get is 1/12. What we get is Ix equal to 1 over 12 h cubed, which is the height, multiplied by the width b. And for Iyy, we get h 1 over 12 h multiplied by b, which is the width, to the power of 3. So as you can see, once you basically take the moment of inertia of Ixx and Yyy, and it's symmetric, just the two, the powers for the b and h interchange. Similarly, you can do for the moment of inertia on Ixy. And if you evaluate that integral, you will see that it's equal to 0. And it's equal to 0 because we have a plane of symmetry. So any cross section where you have at least one plane of symmetry or more, because a cross section can have multiple planes of symmetry, the moment of inertia on xy axis is equal to 0. So you don't have to calculate that. You can basically know this just by looking at it, by inspecting the geometry and noticing this. We have a symmetric axis, and we can set it equal to 0. And that's sufficient explanation also doing exams and other problems. Just state, due to symmetry, Ixy is equal to 0. So if we do this, what we get is these three equations for our rectangular cross section. And the benefit is that these rectangular cross section or these equations are valid around the centroidal axis. So if we actually change our centroidal axis, say from the centroid to one of the corners, say the bottom left corner, then technically we have to change the equation again. We have to reevaluate the equations, etc. However, we get one easy way out. We can use what's called well, we'll get to that later. So the moment of inertia on centroidal axis are basically well-known properties for different cross sections, and these are often given in handbooks. So we get for a rectangle, for a triangle, for a semicircle, quarter circle, circle, and ellipsoid. And this is these are all solids, but they can also be non-solid cross sections. So if you look in books, often these moment of inertias are given. So it would be nice if we had in theory or some trick that we could use these known values and then basically do something with them so we can basically transfer it to a different axis. There's where the parallel axis theorem comes from. What we basically do is we say, okay, we want to have our moment of inertia on a different axis system than the centroidal. So what we do is we use the what's called the Steiner theorem, which basically refers to that the centroid, if you take the moment of inertia on centroidal axis and reposition that to a different axis, you can keep the moment of inertia is equal to the moment of inertia of your centroidal axis system. So Ixxc plus the area of your cross section multiplied by the distance to your new reference systems squared. So in this case, there will be see at the mouse, if this is your centroid and you have your moment of inertia defined around your centroid, that would mean that Ixx is equal to Ixxc around the centroid plus the area of the cross section multiplied by d squared. So in this case, your moment of inertia around your x dash system is equal to Ixx around your centroidal axis plus ad squared. And this is known as Steiner's theorem or the parallel axis theorem. And we can basically use that to get the moment of inertia on different axis systems very quickly. So instead of recalculating the integral like we do here in this slide, so instead of changing the bounds from 0 to b and 0 to h, so we get the moment of inertia on point A, if we evaluate that, we get 1/3 h cubed multiplied by b. And if we use the Steiner's theorem, what we see is we get the moment of inertia around point A is equal to the moment of inertia around C, which is centroid plus AD squared. So around the centroid was a given because those are like standard shapes. So we know it's 1/12 h cubed b. So we add the AD term. A is equal to h times b, that's area, and the D term is equal to h over 2 squared. So if we evaluate that, we get the same equation as our integral. We get the same answer as our integral equation. And the difference is this is significantly faster to do this kind of calculations instead of just every time re-evaluating the integral. So, and that's where basically we stopped. So the next point where we're going to continue is talking about something that we already mentioned earlier, was in aerospace structures we can often ignore one of the thicknesses. We can assume that one of the thicknesses, one of the dimensions is significantly smaller than the other two, and therefore we could, in our plane stress condition, if you remember that correctly from our stresses, we said, well, the thickness is significantly smaller than the length or the width. And because of that, we said, because of this, we can say that there's no variation of stresses in the z direction if z is aligned with the thickness, and therefore we said sigma z is equal to 0, and shear stress in xz and shear stress in yz are also equal to 0. And this, as a consequence, meant also automatically that shear strains and yz and xz are also equal to 0. So we can do a similar assumption as this. That's basically known as a thin walled assumption. And it's very common in aerospace structures to use that assumption because, like I said, majority of the time, the thickness, especially the thickness direction, is significantly smaller in dimension or in value of magnitude than the length and width. So there's where the thin walled assumption comes in. So this was basically from a stress point of view. From a cross-sectional point of view, we call basically a similar assumption that we make is called a thin walled assumption. And for the thin wall assumption, we say whenever we have t is equal or greater than t squared, we assume it's equal to be 0. So whenever we see a t squared or above in our equations, we say that that component or that contribution of that part is equal to 0. So what does that mean for our square, for example? So in this case, if you look back at our equations here, so this was, say, thick walled. And if it's thin walled, then we see that Ixx, Iyy, Ixy, Ixy is easy because that means 0. So let's have a look at this equation. This is actually not a good this is actually not a good example. Let's do a different example because this one is not good. This is a thick walled, or this is a solid, and we need to look at basically something which is a wall thickness. So let's look at a different thing. We again take a rectangular. We again do it around the centroid. So we know it's in the middle based on symmetry. It's in the middle. We have our x-axis. We have our y-axis. We call this thickness T. We call this B. We call this H. Yeah. So, and the rest is basically a hollow, okay? So, let's do that a bit better. Let's call it like this. Okay. Well, this is our cross section. Now, let's do the moment of inertia from this section. We said earlier that the moment of inertia is basically a contribution of the different segments. So what we can say is, well, we have a segment here. Basically split up into 4 segments. Let's call this the green area. Here we have also a green area. And then we have a purple area. So here, green here. So the moment of inertia of the cross section is equal to around x. We can say twice the moment of inertia of the green section around x plus twice the moment of inertia around the purple section. So let's evaluate. So we recall our standard equation for a rectangle. So we know the moment of inertia around x is 1/12 b h cubed over v. So that's for when you have something like this. And then we have 1/12 b cubed, and this one is like flat. And these two contributions we use, okay? Remember, this always with respect to its own centroid. So this is centroid from the bottom one, and this is centroid from the green one, okay? So let's evaluate that. So what do we have here? So we have here for the green section. So we take the 2 out of the part, so we get 2. So for the green section, we get 1/12. The h, this is still h, so that's h. And this case, the width is not b, but that's equal to t. Okay? So we get t here, and this was h cubed. So of course, this is the moment of inertia around this axis system. So it technically is aligned with the centroidal axis system, so they coincide. So basically, yes, in theory you will have an AD term, which is h times t, but then the difference between the axis, the parallel axis, the d term is equal to 0. So that's 0 squared. Let's just put that in there anyways. So we do the same for the purple section. There's the black ones. And we repeat for the purple section. We again have this equation for the moment of inertia. So we get 1/12. So what's the width in this case? It's basically b minus 2t. That's here. That's b minus 2t to the power of 3. And then we get multiplied by h. That's equal to the thickness as well. So that's t. And then we get basically, let's make a lot of bit. So plus the area, so that's basically b minus 2t multiplied by h multiplied by the distance squared. So that be technically, if this is h over 2, so we get h over 2 minus t over 2, because the centroid is in the middle. So this will be officially our moment of inertia for this cross section. And then let's see if we can simplify a bit. So that 0 drops at least. Let me see. Wait, this is squared here. Okay. So we get 1/6 h cubed t. This is 0, so that drops. This is 1/6 again. So we have to expand this. It's b over 2t. So we get B cubed. Let's do the big easy. Cubed minus 4bt plus 4t squared. So b cubed, this is a bracket here, minus b to the power 3t4 plus b 4bt squared minus 2bt this minus 8bt squared minus 8t to the power 3. Give the 2 here as well. So plus 2 times this. So we get here is BH, TH, and this is right here, this is H, 1 over 4, let's take that out of brackets, H squared minus 2TH plus T squared. So this. We get B, so we get 1 over 4, so we take that out, so we get 1 over 2. B H to the power 3 minus 2TH cubed B minus plus BH T squared then we get minus 2H power 3 minus 4T squared H squared minus 2T squared T to the power 3H. So this will be technically your moment of inertia if you do it using a thick wall assumption, where you say that thickness, where you don't make any assumptions out of it. So if you can see, quite complicated, and if you would calculate the difference in moment of inertia, say thick wall versus thin wall, you see that the difference is delta is less than 0.1%, even less. So you can basically ignore that. So, and why does that? Why does it make sense? Well, this is the reason why it makes sense if we do both. So, in order to avoid this complicated equation, what we basically say this structure is no longer thick walled. We say it's thin walled. So now we basically say this is equivalent to this structure where we have H, we have thickness everywhere, and we have B here. So if we now do the same calculation from the moment of inertia, we again have equal to 2 times 1 over 12 H to the power 3 times T plus 2 times 1 over 12, and then here we have the thickness, power 3 times C. Oh wait, no, this is B, so we have B to the power 3 times T plus the standard term, in this case will be BT multiplied by H squared, H over 2 minus, well, squared, not minus anything. So what we do is, we basically say, we take the T components, where is everything equal to power of 2 and higher. We basically ignore those components. So this one is ignored, this one is ignored, this one is ignored, And let me see. This one is ignored. This one is ignored. This one is ignored. So we basically reduce the complexity of our equation, and then what we get is something like this. So what we now did is, instead of having to deal with the expansion of the equations, probably I've made a mistake in the expansion, so you can double check that on your own. But what we do is we basically reduce this component to a thin wall. So we basically then assume that the centroid of this top part lies basically on the thickness itself here as well. So we no longer take into account the thickness effect. We just say the difference from the centroidal axis to this given coordinate system or local axis, local centroid, is just the distance of h over 2. And this simplifies our equations significantly, especially if you compare this to this. And probably, let me see, where did this come from? This 1/6. Like I said, I made a mistake here, so let me see that back. So it's okay. Yeah, this t. So yeah, okay. I missed this t, by the way. So this should be b to the power b cubed to the power of 3. So this becomes a b t squared. This becomes a t to the power of 3. This becomes a t squared. This 3, and this one is a 4. So that's these two also drop out. So this is similar to this what we have here, and this one will become bth squared over power 4. And we probably see that popping up as well. You see? Yeah. So 4, so multiply by 2, so it becomes over 2. So probably here I missed also a t somewhere. Yeah. So I should have done this expansion a bit better. What we get here is t over 2 squared minus 2 times t 4h plus t squared over 4 multiplied by bh minus 2th. So we get power of 3 here. If you do it correctly, it drops out. So like I said, as you can see, even I make mistakes. So especially when you don't take the thin wall assumption into account, you have to basically deal up with all the expansion of the different components. I see this even not visible on screen. So you have to deal with the expansion of the components, which would make easily errors and just make your life more difficult. So let me see. Yeah, it was not visible. So I'm gonna just repeat the thin wall part of it on this side of the board, so it's visible for those online as well. So quick recap. We said using the thin wall assumption, if we have a certain width b, certain height, and wall thickness t, we can basically say it's equivalent to this structure. We have b, h, and t. So in cases, say for example the bottom part, this part, the centroid no longer lies at say b minus t over 2, but it lies just at, or the central axis from the centroid to the local coordinate system is no longer h over 2 minus t over 2. but it's just the difference from this axis, from the coordinates centroidal axis to the local centroid is just h over 2. So that's the implication of that assumption as well. So if you then just do the moment of inertia, you can say Ixx of the cross section is equal to 1/12 multiplied by h squared, h to the power 3 times t times 2, so 2 over 12 plus twice the contribution of these two top and bottom, which is 1 over 12 b cubed t, because the height is equal to thickness, plus the AD term, so that's b times t multiplied by h squared over 4. So it simplifies the equation. Good. And if you would basically plug in realistic values for the thick walled and thin walled, the differences are extremely small. Yes?
So is there a thickness to width or thickness to height ratio we could look up to, or like let's say we have a problem that says thickness is 2 millimeters?
Yeah, that's a good question. So yes, this is valid under given conditions. So just like your plane stress, we didn't discuss that, but it's often valid if your say your thickness is often indicated like this, significantly smaller than the width or length, and we are talking about a factor of like 10 or more. So if your height is say 10 units and your thickness is 1, you can use it. But if you, of course, if your thickness, let's assume we have these two. So this is one cross section and this is the second cross section. Then in your first cross section, you cannot use it because actually, if you now calculate the difference between thick walled and thin walled of Ixx, thick versus. So for cross section number 1, that difference would be at least, I would say, 25%, while for cross section number 2, it's probably 0.1%. So here you can ignore it. Here you can ignore it. For cross section 1, you cannot ignore it.
The rule of thumb is
it's approximately 10 times the magnitude. So if you would do t of t over h or h over t, if that's larger than 10, or w over t larger than 10. In most cases, with aerospace structures, if it's not explicitly mentioned as a thick wall assumption, as a thick wall structure, you can use the thin wall assumption.
it's not mentioned it's a thick wall because you want them.
Yeah. You're free to always make assumptions to make your life easier. You just have to make sure that you, if it's not mentioned anywhere, that you mention yourself that you use a thin wall assumption or a plane stress or plane strain. But often from the problem, say for example in the stress problems, if it's a 2D stress problem, then you can often assume one of the dimensions already being ignored. Let's do a couple of examples. This case again, I think it's one of the book examples as well. I'll give you a couple of minutes to do it, and then we do it together. So you have a C section with B and height 2h. So height is h. This is our x-axis. This is our y-axis, and our central lies somewhere here. The thickness is equal to t, and it's uniform for the cross section. And the assignment is calculate the moment of inertia xx around your centroid. So I'll give you guys a couple of minutes to do this, and then we continue doing this together. Okay. So what we do is, again, calculate the moment of inertia. We basically split up in 3 parts. We say the moment of inertia is around the top, indicated by t, plus the moment of inertia around x for the bottom, plus the moment of inertia around x for the web. And then we can use our standardized formulas that we got. We assume it's involved as well, simultaneously. So what we get is 1 over 12 2h to the power of 3 times t plus, and these two, that's the web, by the way. And yeah, let's do it in order. So we know based on symmetry, so moment of inertia around x, y is equal to 0, but also based on symmetry, we know that Ixx from the top is equal to the Ixx from the bottom. So we can just multiply that by 2. So we get 2 here. So this is Ixx of the bottom. Let's use that. So that's 1/12 b cubed multiplied by t. Then we have to add a standard term to it. So that's bt and then h squared. So this is valid for the top, for the bottom, and also for the top. To be 100% correct, you should say it's minus h squared, but the squared makes positive. And then we add the moment of inertia of the web to it, and that's where we get 1/12 2h to the power of 3 multiplied by t, which is the thickness and the width of the section. And then we can, if we want to simplify it a bit, so what we get is, can we simplify it? Yeah, we can take a bt out of it. So we can bt out of this part, and then we get 1 over 6 b squared. Take a bt out of it. This is a plus, by the way, plus 2h squared. And here what we get is 8 over 12. So we get 3 over 4. 2 over 3. We can simplify if we want to. It's not necessarily. Sometimes if you simplify it, it might be easier since things will drop. Yes?
So on the Webb's thickness, Webb's moment of inertia, do we not do the parallel axis theorem if we're taking a moment around C?
Not for X. So let's have a look at it. It's a good question. So let's call this this our web axis, right? Mm-hmm. So the centroid of the web line coincides with the centroid of the cross section.
Oh, okay. So as long as it's on that.
Yeah. So basically, if you would, there is no d term to it. So basically, in this case, the a times d squared, the d term is 0. In this case, d is equal to 0.
Okay.
For the bottom, then you have this. This is your d, and that's in this case h. So if you want to do the moment of inertia on y, now what you get is, we can do that. Just say let's do the moment of inertia on y as well. And I will not do the full calculations. So what we get is, in this case, let's do the web first. So we do web and then bottom, top, and bottom. B, capital T, and capital W. Okay. So we do again the same thing. It's equal to the top, the bottom, and the web. In this case, we get 2 times. Now we get 1 over 12. And then if you do the moment of inertia, we basically said, say the moment of inertia is h cubed b. But if it's like basically on the bottom, we get b to the power of 3 times h. So we get is, this was b cubed times h. And in this case, say, let's do it a bit more accurate. centroid of the cross section lies here, and the centroid of the bottom lies there, and this is centroid of the top, and this is centroid of the web, right? So we're now not looking the vertical axis, but we're looking basically in the x direction. So technically, you have to calculate your x coordinate of your centroid. So that's the first step actually when you have when the centroid is unknown for, depending on the problem, when the centroid is unknown, you often have to calculate the centroid location. Say, for example, if this is just a problem where you only have to solve, you have to use moment of inertia xx for it, then you don't have to calculate the centroid because you're not going to use it anyways, right? Because in this case, the centroid only, because the y component is easy, that's h, but the x component is not equal to something that you can easily get out of it. Let's call it cx for now. So basically, in this case, we have this, and then we have to add the standard term to it. So that's b times t, multiplied by that's area, and the distance is basically, in this case, it will be b over 2 minus, let me see, is that correct? Now we go to the left. It doesn't actually matter. So we get xc minus b over 2 squared. Because we're going to go basically to the left. That's your moment of inertia from the top and bottom, including the shift. And then if you do the moment of inertia of the web, you get 1/12, and this is again b cubed h. So you get t cubed multiplied by 2h plus the standard term, so that's 2h t plus, in this case, this will be the distance you shift is just, if you take the coordinate system, if you calculate with respect to 0, 0, if you calculate xc with respect to 0, 0, then this is basically xc squared. So you multiply by xc squared. And then you can say, well, this is t to the power of 2 and higher, so this one drops out, so this becomes 0. So this is now your moment of inertia term.
So basically, it gets a lot more complicated whenever at least in this case, whenever you do with respect to y-axis.
Yeah.
Okay.
So the reason why in this example is actually not, this is from the book example where they do an asymmetric bending case, and the y term doesn't show up. But if you have an example where, say for example, there's a C-section like this, and you have to calculate the direct stresses around with moments around x and moments around y. Then yes, then you have to calculate both. Then in this equation, when we come to that, start in next lecture, we will start driving this. The contribution of IYY and IXX show up, and then you have to calculate both.
Could you clarify the Steiner factor on IYY real quick, like the XC minus B over 2?
Yeah, so you have to always say, how do the shift occur? So this is basically your centroid here, and I go from my centroid of your local axis system to the centroid of the cross section. So in this case, you go to the left, which is, if this is positive defined, so yx. So you're going from CB to the left. So you basically take CB minus, this is actually, should be B over 2 minus CX.
Okay, yeah, that makes sense.
Yes. So because you go to the left, so you go from plus to negative.
Yeah.
Other side will be positive.
Right, yeah, that makes sense.
Yeah, good spotted. And in this case, it will be equal to basically negative CX.
So
because you go from here to there.
if the C structure was tilted up to where it looked more like a U, and we found the moment area with respect to Y, would that be the same equation, but with just different variables as IXX?
Yeah. Okay. Yeah. about it, you always want to take the simplest way out. So anytime you see a structure where it's basically just straight sections, you can always use the easy, well-known parameters of the moment of inertia, like the formulas. And those two are always, like this one. So it's always good to know these two by heart. 1 over 12 b times h cubed, and yy is equal to 1 over 12 b cubed h. Those two are always good to know, and they correspond to something like this. B and h is our rectangle, right? And then, of course, if it's thickness, then the b becomes a t. If h is 2h, then it becomes 2h to the power of 3, etc. So just be careful when it's a 2h. You take 2h to the power of 3, not just the h part component. This is a full length to the power of 3. Okay? So these two are always easy to use, and then together with this time term, we basically can solve 95% of the problems. So again, I gave you an example earlier, something like this. With these two equations plus the standard terms, you can solve this problem. The key component is when the centroid is not basically known by inspection. Basically, you cannot look at this picture and then say it's centralized in the middle or centralized at this location or that location. You have to calculate the centroid first. So calculate centroid first. And then you calculate moment of inertias. So when you have always simple stuff, you can basically decompose to straight sections, which are rectangles basically on a vertical and horizontal. Go for this. And now there comes the question, okay, when is the integral equation slightly better? So basically anything else than this, then the integral equation becomes the way to go. Let me see. And we have been following, this is I think from problem 16.6. And we'll come to that chapter in starting the next lecture series. So we have this cross section, and we have to calculate the centroid, the moment of inertia as well for that given problem. This is y, this is x. So again, normally you have to calculate the centroid, but you can say immediately see by inspection that the centroid will lie at this location C. You can say it's anti-axis metric. So you can say that as well for the centroid. So now, how do we solve this? So let me see what the dimensions are. A. Okay. So this is A. This is A. This is A. And this part is A as well. So now we basically have to calculate the centroid. So no, you cannot just use 1/12 over, say, okay, for the incline. Yeah, so let's call this the incline, and this is the top and bottom. We cannot say it's equal to 1 over 12 of thickness is everywhere T. Let's get that in there as well. So 2a to the power of 3 multiplied by T multiplied by sine 60, because this angle is given as 60. You cannot do this. Okay? Be careful about that. A lot of people do that. So it's not as easy, even though moment of inertia, you can basically add and subtract, you cannot basically rotate given an angle, do an angle transformation. What you have to do is, you have to start off, in this case, from the integral formulation. So recall the integral, Ixx is equal to the integral of y squared dA. So this is for the web part. For the top flange and bottom flange, we can still use this one because it's still basically a rectangle on its belly, horizontal, and then we do a superposition using standard terms. So okay, so let's start with the inclined version. So in this case, what's y equal to? And then, of course, you have to always calculate with respect to the centroid. So your starting bound, your bounds must be determined with respect to the centroid. So we know we're going to travel from minus A to A. So we already have our bounds. Actually, yeah. So what's dA? dA is, of course, dx dy. So the x bound is basically from 0 to t. And then we have our y bound, so we get just t here. It goes from minus a to a. So what's y defined as? That's equal to as basically as if you go along this segment, and we call this segment s, as the path s go, s so multiplied by sine 60, and this is squared. And then your bond changes from dy to ds, and the bonds are from minus a to a. Yep. Okay, so we now basically can evaluate this integral. So if we evaluate this, what we get is t minus a to a s squared multiplied by sine squared 60 ds. We do an integration with respect to ds, so not with theta, so we don't have to deal with the sine squared. But you all know what it is, right? So minus a to a, and then we get 1 over 3 s to the power 3 sine squared 60. So far, so good. And then if we, so we already took the integral, and then we evaluate this at minus a to a. So we get over t over 3. And then s becomes a cubed multiplied by sine squared 60. So that will be your moment of inertia from the inclined section. So that's one part, and the second part from the webs, we still can use our standard equation. That will be 1 over 12 multiplied by a multiplied by t to the power of a to the power of 3 multiplied by t plus there. So that one drops, and then we get the AD term. So that's plus a times t multiplied by, and this height, that's equal to a sine 60 squared. So this drops because you have the power of t, and this becomes a power 3t sine 60. See, is that correct? That's correct. And then you can do the same for the y, and then you basically take the x component, and then you just have to realize x is equal to a or s cosine 60 ds, because now you have to basically take the x component.
Why did a sine 60 squared should it not be just why did this squared?
This one here?
Yeah.
That's your AD term. So
AD squared, yeah.
So that's this horizontal distance. And I want to highlight this as well. Like if you look at Maxon, there's actually problem 16.6 in the current book, and how he does it, he gives for the inclined section, and he says it's this equal to a to the power 3 multiply sine squared 60 over 12 plus 2 times ta a squared sine squared 60. So that's a standard term of the bottom part. Indeed, 2 times because you have to deal with the top and bottom, right? So by inspection, this looks very similar to this equation, right? To our standardized equation. And there's apparently a trick. It's on the formula sheet. I don't advise you to use it. It's sometimes can be confusing. So it says if you have your rectangle and it's you have a given rotation axis of alpha, then the moment of inertia is defined as this part, this moment of inertia is equal to, by the way, this is D and this is B. Then it says the moment of inertia is B times D over 12 multiplied by D squared cosine squared alpha plus B squared sine squared alpha. So this is a similar equation to this. It's given on a formula sheet, but often I would just do the integral format. It's slightly simpler, and then you don't get confused which axis to use. I think, yeah. So that's how Maxon does it. He uses this formula. In this case, he says basically B is equal to thickness, so this is the thickness squared. So this drops out, and you basically have to, let me see, yeah, and in this case, alpha is not 60, but alpha is 30 degrees, how it's orientated, and coincidentally, cosine squared 30 is equal to sine squared 60. So he also doesn't explain that step. So it's, yeah, and there are plenty more of plus b squared alpha. Yeah, it's not good. So there are a lot of these stuff that Clemson does, tricks like this, and he doesn't explain it. So it can become very confusing if you look at the solution manual. So just keep that in mind. And there are a couple of other things we will basically hit our head against, and I will explain those when we hit those as well. So for the last couple of slides, just bear with me a couple of more minutes. We go to the lecture slides recording again, and we go a bit quicker to finish this. And this also on lecture slides. And this equation we see on this slide is also on the formula sheet, so if you want to use it. So finally, say if you go to an even more complex solution, we can always break it down to simple stuff that we know. Say, for example, again, the centroid of an arc circle or half a circle is known. So what we do is we find the centroid from the overall geometry. By inspection, we immediately know it's in the middle, so that's easy. Then we find we calculate the moment of inertia from the individual components, and we basically translate that to our centroidal axis. So in this case, what we do is we split up into two segments, the top and the bottom, and we calculate the moment of inertia on this point, which is the centroid of our the center of our circle, because that's a known value, and then we just basically translate that to our centroidal axis of the geometry. And then we can do that. In this case, for the A section, we know cross section over A. Again, if you do the full integral, we do a small coordinate transformation. We go from x and y to d theta dt. We calculate the moment of inertia. Basically, you can memorize moment of inertia of a half circle is equal to pi multiplied by radius t over 2. And then we basically apply the standard terms, and then we multiply by 2 because we have two of these. So we go from a complex problem that might seem intimidating to the basics that we understand as cross sections around their own centroid or own center, and then we add a standard term to it to translate, and then we know we have a top and bottom, they're symmetric, so we can basically add that together. Yeah.
In the slides, it comments on 16.2 cross-section is not symmetric. And why is it not? Yeah, that one. Just back one.
Yeah. Can you place a mirror and you get the same solution? It's not exactly symmetric.
In what way?
So if you would say mirror it here, then you get like circle going like this, right? So if you mirror it on this, then the circles again, not the exact same thing.
Okay.
So it's axisymmetric, but not symmetric. So you can only say moment of inertia around xy0 when it's a full symmetry plane. So in this case, you call this axisymmetric. It's not, you don't apply that for the moment of inertia. And because it's not symmetric, so this is we have to do is we have to calculate the direct stresses, and because we have a non-symmetric cross section, we get non-symmetric bending, and therefore all the three components, as we'll see in starting the next lecture, will pop up. The moment of inertia of x, xx, yy, and xy will pop up. So you can just continue for one section and multiply by 2. And there are a couple of last remarks as well. Some additional slides is basically saying the same thing. Moment of inertia can be subtracted, added or subtracted. And some definition of other terms of a moment of inertia you probably know of. So mass moment of inertia is basically when we're talking about rotating bodies with respect to motion. Units, often the units basically give away what we're talking about. So in this case, kilograms meters squared, and the second moment of area, units to the power 4. That's what we're basically talking about. And then you also have there's again angular momentum. First moment of area, basically if you want to calculate centroid. And then the polar moment of inertia, this comes often into effect when we're talking about torsional sections. And one of the relationships for moment of inertia, torsional moment of inertia is equals to Ixx plus Yyy. And then the polar moment of inertia, when we go to circles, we often relate that to the polar moment of inertia instead of just moment of inertia. And what you do here is same thing. We just what we do is instead of dealing with x and y, we do a coordinate transformation to theta and dt. So we basically say x is equal to r cosine theta, where r is the radius, and y is equal to r sine theta. And then our dA becomes nothing else than basically dr d theta. So dA is basically defined as r times dr d theta. So now your equations, you do a coordinate transformation, and now your dA is basically replaced by r dr d theta. But we will go to those equations later on as well. Okay, thank you very much. Are there any questions? Okay, good.